Hi, my name is Kendall Perry, and along with my teammates Hanju Kim, Alana Homer, and Tim Stern, we make up the Red Shirts. For the past several weeks, we've been working on designing and building a machine that accomplishes the assigned tasks laid out for us by the ME 2110 competition. In the following presentation, we'll take a look at what those tasks are, how we went about the design process, what designs we decided to pursue, and how the final product performed in testing and in competition. Finally, we will analyze these results and talk about the conclusions we came to as a result of our experience. Our mission was to go to Mars and thrive. That is, a 7-foot by 7-foot Mars, saturated with tennis balls, squash balls, plastic rocks, and 3D printed astronauts and rovers. Our goal was to design and build a robot that could perform 5 separate tasks. The tasks were worth a varying amount of points and placed at separate locations around the track. In order to properly start designing machines capable of completing these tasks, we started with a house of quality, laying out the customer requirements shown on the left and the engineering requirements shown above. One of the most important things we noticed in doing this was the importance of multiple functions and the negative effects this had on every other engineering requirement. Next, we noticed that scoring positive points and preventing negative points, along with being consistent and effective, strongly correlated with the engineering requirement that the machine execute consistently, actually making it our most important engineering requirement. As we will see, these relationships did indeed turn out to be the case, and unfortunately, we paid dearly for it. Outside of the basic specifications that were laid out by the competition rules, there are 3 specifications that we focused on early, and that we will see were important to how we performed later in the competition. The first of these was trying to score over 175 points. The second was having a failure rate of less than 1%, and the third and final one was the mechanism lasts more than 150 uses. Of course, these were wishes and not demands, but they still proved to be ambitious in hindsight. While we obviously wanted to accomplish all of the tasks at some point, we determined that the 3 most important tasks were those involving the mountain ridge, and therefore focused on those in most of our initial designs, deciding to add the functions that accomplish gathering the rocks and clearing the radioactive elements later on. The mountain ridge tasks also had the advantage of being placed closely together, so by aiming for these, we would not be using up as much space on the machine. Using a morphological chart, we laid out different ways of accomplishing the 5 tasks and put together several different designs using different combination of these methods. The designs we ended up using are highlighted in this chart. From the morph chart, our first alternative design lacks both the spacecraft subsystem and an astronaut and rover subsystem. It's probably obvious that this will not score highly on the evaluation matrix because of this. Our second design alternative is a cart system to reach out to the mountain ridge, but we were concerned that the interference from other machines in a competition setting could disrupt the cart, thus inhibiting us from performing all 3 mountain ridge tasks. This was simply too risky. The third design alternative was unique in its orientation, and it could also reach out to the mountain ridge very quickly using pneumatics, but we had big doubts over how consistent a system like this would be. The fourth design alternative uses pneumatic cylinders to reach out and place the flag and gather the rocks, but in many ways it's just a less space-efficient version of our selected design. The selected design does not depend on any mechatronic or pneumatic devices to reach out to the mountain ridge, except using a solenoid as a trigger. Its declining draw sliders with mechanisms rely on gravity to reach out to the mountain ridge, thus being far more consistent and reliable. Analyzing these designs using an evaluation matrix, it is clear to see why the selected design won out. The absence of pneumatics dramatically reduces setup time and ease. By relying on gravity as a uniform force, greatly improves consistency. After some tweaking and the addition of the radioactive element arm, this is our final design. It looks busy, but is actually very space efficient as it achieves all 5 functions. This is what the final design looks like when it's fully deployed, with each function in its final resting state. The astronaut and rover rescue arm is attached to the main draw sliders on the machine. The draw sliders are released by a vertically orientated solenoid, which when activated removes the stopper holding them back. As the draw sliders slide out, a pin is removed from the mouse strap to which the arm is attached. The flag placement arm worked almost identically, flipping forward when a separate pin was pulled and staying in place due to Velcro. The spacecraft landing subsystem employed another vertically orientated solenoid mechanism. When the switch was pressed twice in quick succession, indicating a safe zone, the solenoid would be activated, releasing the ramp and allowing the spacecraft to roll into the safe zone. Once the draw sliders were extended, the rock collecting arm was designed to fall under its own weight. A radius curved into the base plate meant that when pulled on by a motor, it would sweep around the front of the machine. The motor itself is mounted onto an extended arm which falls away from the machine when the motor starts spinning, allowing the arm to pull the rocks all the way back onto the home plate. The radioactive clearing cart works by extending a vertical scissor arm to push a cart with extending arms onto the center of the track. The release mechanism for the weight that powered the scissor arm was by far one of the most challenging obstacles we encountered when building this machine. We finally settled on a motor that would pull a pin away from the weight to release the arm. At this point, the arms proceed to fall under their own weight and push the tennis balls out of our home zone. Here we have a clip of the entire machine functioning as it should. This was taken after the competition. Unfortunately, it didn't work like this on the day, but we wanted to make a point that it does work. Just about. There's a long pause before the radioactive element clearing arm extends. This is intentional. It was coded to deploy 35 seconds into the round so that we could have the final say when it came to whose zone the tennis balls were in. Pre-qualifying testing revealed that while the flag arm and the spacecraft landing were working 100% of the time, the astronaut and rover retrieval arm was not working perfectly, as the astronauts and rovers would sometimes bounce into the accompanying hostile home zones. Similarly, the rock collection arm was only working with partial success, only collecting all 3 rocks about 30% of the time. The radioactive clearing subsystem had not been added at this point. Before pre-final testing, the rock collecting arm had undergone minor changes so that it was more reliable and consistent, retrieving 3 rocks and maybe some partials per round. All other mechanisms, including the flag arm, rover and astronaut arm, and the spacecraft deposit systems were working and acquiring points consistently as they were before. The radioactive clearing subsystem was built last on top of the already existing functions, and this subsystem in particular ran into many spacing and interference problems during the building phase, with the unfortunate consequence that it could not be tested, nor could the fully integrated machine be tested, simply due to a lack of time. This would later prove to be one of the most important reasons for our disappointing performance in the final competition. In the final competition, we were given a bye through round 1 as a result of seeding. In round 2, we were disqualified due to failing to box the machine in time. The machine did fit into the box, but it was continually being triggered as a result of coming into contact with the inside of the box. This was down to the addition of the radioactive element clearing arm, as minor size adjustments had to be made to numerous other parts of the machine to accommodate it. Moving into round 3, as a result of our bye, something had to be done to allow the machine to box, and the decision was taken to strip off the radioactive arm completely. But the damage had already been done, as tweaks made to the other subsystems had caused them to function ever so slightly differently, but these differences would have devastating effects. The flag arm failed to properly position itself now that the Velcro patch holding it was smaller. Likewise, the spacecraft landing mechanism trigger failed to properly position and connect with the safety zone beacons. What had previously been extremely consistent functions failed as a result of lack of testing after modification. What we had previously thought were 120 guaranteed points was sorely missed. Looking back on the final competition qualifying rounds, it was obvious that our performance suffered for 2 main reasons. Building took longer than anticipated, and the fully integrated machine was subsequently tested little to none at all. We paid dearly for this, and now recognize the mistake of trying to achieve better results without properly testing and improving our already finished subsystems. We should have been more willing to pull the plug on the radioactive clearing subsystem when it was clear it was taking too long to build. Given the opportunity to redo the week leading up to the competition, it is likely that more attention would have been given to simply improving and testing the 4 functions we had already built, ensuring their ability to perform reliably and consistently in the final competition. In conclusion, while we'd love to go back and do it all over again, maybe even getting some better results along the way, we hope that the lessons we learned are far more valuable in the long run than winning ever could have been. Sometimes it's better to cut off something that's no benefit to you, no matter how hard you worked on it. Had we chosen to leave off the radioactive clearing subsystem, we'd have saved ourselves 30 hours of building, properly tested our other subsystems, and Hanji wouldn't have PTSD right now. Our greed for more points caused us to actually garner fewer points. We know that now. However, despite crashing and burning in the final competition, we did have fun in this class, and would like to especially thank Dr. D, all the TAs who helped to keep the studio open for late night building sessions, and everyone involved in making ME2110 a truly unique class experience we will never forget.